All right, so a little section of bonus notes here for you just kind of having here. This would be Wednesday, 21st. And we're going to do basically two things. We're going to do determinants, and we're going to talk about inverses of matrices. So we're not actually going to find the inverses. We're just going to talk about what you can do and kind of how to get there. But we're going to kind of go easy on that part because that's the part to actually find inverses. It digs in, gets a little bit deeper than what we're going to do. But at least that way you kind of had some idea of what's happening here. Okay, so very first thing that we're going to look at is they talk about the multiplicative. It's always a fun word to say. Multiplicative identity matrix. So when they talk about those, they just call it I for short. And depending on the size, now for this one, they only talk about, for these, they talk about with square matrix. So when they talk about I2, basically is this, that you're going to have ones on a diagonal this way, and then all the other numbers would be zero. If it was a 3x3 matrix, again, you put ones on the diagonal here, and then all the other numbers would wind up being zero. So it'd be something like that. You could go on out to like a 4x4 or a 5x5 to do these, but that just gets too big, and we're not going to do anything that's that big. But that's basically all you do. Just if we were expanding this out to a 4x4, you'd have these on a diagonal, and then everything else around it would be zeros. So that's what the identity matrix looks like, or multiplicative identity matrix. Okay, and then what they kind of say is this one when we're going through these, that if you multiply two matrices together, if you do A times B, and that equals the identity matrix, then what they'll say is that matrix B is the multiplicative identity, or the multiplicative inverse of A. So if you multiply A times B and you get the identity matrix, then matrix B is the multiplicative inverse of A. All right, and they'll show that with A negative 1 if it's the inverse. And if you remember when we did functions not too long ago, when we were doing functions, we also talked about inverses of functions there. And that one, they used the same notation. They used F negative 1 when we talked about functions. So inverses, they talk about the same thing, that it's A negative 1 to know that that's the inverse of whatever matrix A was. Okay, so one of the things they're going to ask you to do is we'll do something like this just so we can kind of see what's here. They may ask you, are A and B inverse matrices? And of course, they have to tell you what those two matrices are. Okay, so there's two matrices we're going to use in this case. So A is 1, 1, 5, 4, and then B is negative 4, 1, 5, negative 1. Okay, so again, to figure out if they're inverse matrices or not, we just multiply them together. And since they're both 2 by 2 matrices, if we get 1, 0, 0, 1 when we finish with those two, then it is. If we get anything else, then it's not going to be that way. All right, so we're going to do A times B. All right, and remember, going back and kind of reviewing what we were doing yesterday, we're going to multiply these together. The first thing is we're going to take row 1, which was the A matrix. So we're going to take the rows out of matrix A and multiply that times the columns of B. So we're going to take the first row that's here and multiply it by the first column here. So that's 1, 1 times negative 4, 5. Okay, and I think most everybody was here may have had 1 or 2 people out yesterday. That when we're doing these, again, it's always the rows of the first matrix by the columns of the second matrix. And from there, you just multiply the numbers together. It's 1 times negative 4, which is negative 4. Then we add that to the next two numbers multiplied together. Then it's 1 times 5, which would be 5. So that would be 1. All right, so if we keep up with this thing and see if it's going to work out. There was the one that we've got right here, so we'll put that one in here. All right, and we're going to stay with row 1 here. So we've got this row times this column. We also have to take this row and multiply it by the second column. So that's going to be 1, 1 times 1, negative 1. Okay, so that's 1 times 1, which is 1. And then we're going to add that to 1 times negative 1. And that would be 0. Okay, so far so good. So we've got 1, 0 on this one. If the next numbers are 0, 1, then we've got what would be the inverse of it. All right, so we've done everything with row 1. We've taken row 1 and we've multiplied it by column 1 and column 2. We're out of columns. So now we've got to go to row 2. So we're going to take row 2. So row 2 of A. So and we're going to multiply that by the first column and then by the second column. Okay, so now we're going to do 5, 4 times negative 4, 5. All right, so we got 5 times negative 4 for negative 20. And we're also going to do 4 times 5, which would be just a regular 20. So negative 20 plus 20 would be 0. All right, so far so good. So if we do that last row here with the last column here, if that comes out to be a 1 that we can put here, then we're good to go. So we're going to take the A, we're going to take row 2, and multiply it by B of column 2. That is, let's get that up a little bit so y'all can see it here. So it's going to be 5, 4 times 1, negative 1. All right, so it's 5 times 1 for 5. 4 times negative 1 for negative 4. So if we do 5 plus negative 4, that would be 1. So then we've got the inverse that works here. So they ask us, okay, are those two things inverse matrices? Because we've got the 1s on the diagonal, then yeah, we're good to go. Okay, so I felt good about doing these because it's just an extension of what we were doing yesterday with multiplication. Sometimes, especially with multiplication, I hate just to do one day of it. So this is good because it makes us go back and kind of review it. That again, it's always the rows times the columns when you go through these. All right, let's give you one more here. Just so you can see what one that's not going to be that way. Okay, so same question on this one. Are A and B inverses? This time we'll go matrix A will be at 3, 2, 5, 4. And for matrix B, let's go with 2, -5. Throw a fraction at you just so you what happens here. And then 5, -5 and 2. So don't, and again, I know sometimes you like to freak out when we get to fractions. Most of the fractions you work with here, even if you have a fraction involved with it, it should work its way out, so it won't be too bad. They won't give you anything that's too awfully weird when it comes through most of these. It's usually pretty easy when it comes to it. All right, so we started again. So we're going to do A times B. All right, so again, it's the rows here times the columns here. So we're going to do 3, 2 times 2 and -5/2. Okay, so first number here times first number here, 3 times 2 is 6. And the good thing with this is when we multiply the 2 times the -5/2, the 2's will cancel. So that'll make it -5. So it's 6 plus -5, which would be 1. Okay, so first number is good. We've got a 1 here. Now, if that had been, if that had been a 6 plus 5, if that had been 11, then you'd stop right there and say, all right, that's it. So the first, if we're doing these, if you multiply them together for it to be an inverse, the first number has to be 1. If that had been 6 plus 5 and that number was 11, you could just stop right there and say, no, it's not inverse. But so far, the first number checks out here. So now we got to check the first row times the second column. So we've got 3 times -5 for -15. We're going to add that to 2 plus 2, which is 4, and that is -11. So as soon as we get, and again, that's supposed to be a 0. So as soon as that is not 0, you can stop right there and say, no, it's not inverse. Okay, so again, inverse, it's got to be, if it's a 2 by 2 matrix, it has to be 1, 0, 0, 1. As soon as you get one number that doesn't fit in that pattern, then you just stop and say, all right, that's it. Okay, now, and we didn't worry about doing 3 by 3s because 3 by 3s, it would still be the same thing. It would still be this row times this column, it'd be this row times this column, and then be this row times the next column. It's the same process. It just goes a little bit deeper and makes you do a little bit more with it. Okay, so there's how you check to see if two matrices are inverses of each other. Just multiply them together, and you're looking for ones and zeros so that ones are on that main diagonal and everything else winds up being 0. All right. Okay, so for determinants, and again, math people are usually really good about coming up with shortcuts. They don't like to write out the long word determinant, so that's all right. Just for short, we're going to call it DET. We'll abbreviate it. Okay, so we're going to do determinants of a square matrix. So now we're only going to worry about 2 by 2s, and we're only going to worry about 3 by 3s. If we get anything bigger than that, it just gets to be overkill. It's the same process. Again, it just gets a little bit bigger. So we're going to stick to 2 by 2s and 3 by 3s. All right, so here we go. If A is, and just keeping it real simple on this one, A, B, C, D. Doesn't really matter we're not worried about the numbers. This is more about the setup on this one. That if matrix A is A, B, C, D, then the determinant of A, to get it, is you're going to take the original matrix that you have, which is A, B, C, D, and basically do cross products. Now, the only thing on this one is when you do the cross products, you want to kind of go this way. So you want to do D times A, and then we're going to do minus C times B. And the determinant gives you an actual number from that matrix. And then we'll show you a little bit what you would do with that number and how to kind of get with what it does and how to set it up and do some things with it. But for right now, just know that if we do the determinant of the matrix, it's going to give you a number that's associated with that matrix. And for a 2 by 2 matrix, really simple. You multiply cross products. You go here and here, and it's always this number minus and then this number. All right, so let's show you one here. So let's say A is 2, 5, and then negative 4, 8. Then they should tell you to find the determinant of A. All right, again, for a 2 by 2, really straightforward. It's 8 times 2, which is 16, minus negative 4, 5 times 5, which is negative 20. So if it's 16 minus negative 20, that's really 16 plus 20. That's 36. Okay, so for a 2 by 2 matrix, really straightforward. Just do cross products, and remember, it is a minus sign that's in the middle. And then you subtract those numbers, which in this case it was a minus and negative, which made it a positive number, which will happen on some of these. Add or subtract those numbers together, and that's going to give you the value that you have there. All right, now the one thing they kind of like to add on to that one is they say, all right, if we're doing these determinants, if it's a 2 by 2 matrix when we're going through these, or if it's 3 by 3, really what comes off of it, one little thing we can add to that one is that if the determinant of a matrix doesn't, we're doing determinant A here in this case, but it doesn't really matter what you call it. But anytime you do determinant of a matrix, if it equals 0, the matrix does not have an inverse. Okay, so that's just one little thing that they kind of talk about it. That's one little thing you can kind of put in the back there, that if you're going through and you find one of these and the determinant winds up being 0, then that matrix will not have an inverse. So it's almost like a little check when we're going to go through these. All right, last thing we're going to do is we're going to find the determinant of a 3 by 3 matrix. All right, and how we did, we'll kind of stick with what we did on the last one. We'll do like A, B, C, D, E, F, and then just stay in alphabetical order. We'll do G, H, and I. Most of the time we don't like to use the I for a variable, but in this case we'll just kind of go ahead and stick with it because, again, we know it's not imaginary numbers. It's just a number that's in the matrix on this thing, so don't worry about what it is here. Okay, so if A is this 3 by 3 matrix that you have, here's how we're going to figure out what the determinant of that 3 by 3 matrix is. Leave a little bit of room between this one, so leave a couple lines if you're kind of keeping up with this one. So what we're going to do is we're going to take the determinant of A, because what we're going to do is we're going to take the original problem that you have, A, B, C, the D, E, F, and then the G, H, and the I. So go ahead and rewrite that original matrix that we would have there. And then what you're going to do is you're going to add in these first 2 rows or these first 2 columns. You're going to basically just tack on these first 2 columns again. Okay, so if that's our matrix, what you're going to do to define the determinant is you're going to rewrite the same matrix you have, but then just add on the next two columns. And we're just rewriting it with the first two columns repeated at the end. Or on the side, ever how you want to say it. It doesn't really matter how you say it for this part of it. All right, and here's what we're going to do. I still didn't leave enough room on this thing. Okay, and I left a little bit more room, and I still messed it up with this one. So here's what we're going to do. You're going to do the cross products like we were doing before, but we're going to multiply three numbers because it's 3 by 3 matrix now. So we're going to multiply I times E times A. And I wrote this in here and kind of messed this thing up. So what I'm going to do is I'm going to put this below it here. I'm going to do I times E times A. We're going to add that to G times F times B. And we're going to add that to H times D times C. All right, and just like in the other problem, you had to subtract it. But in this case, because we're going to have more than one number here, we're going to subtract, and we're going to put this thing in parentheses. And then we're going to start going in this direction. Now we're going to go to the right side. So we're going to do G times E times C. Add that to HFA. And we're going to add that to IDB. Okay, now, and it seems like sometimes people were thrown off on this one a little bit because they were like, it seems kind of hard. Once you see one with numbers, it's really not too bad. All right, so here's what we're going to do. All right, so we're going to find the determinant. And again, leave a little bit of room here. We'll make sure I leave plenty of room up here for this one because we're going to do all the work above it, just kind of like we're doing here. And we're just going to do it one time so we can kind of keep up with it, so we won't have to do too much work here. Let's do 103, 246, and 5, negative 1, 3. Okay, so we're going to find the determinant of this matrix. And again, I'm leaving a lot of room here so we can go back and kind of do it all with this part what's here. All right, just so we don't have to rewrite this thing one more time. This is the matrix we've got to find. A lot of times they'll just put, DET out beside it, and they'll have you kind of go from here. Then all we're going to do is, again, we're going to take these first two columns that we have and just rewrite them one more time. So this was the problem, and then to actually work it out, we're just going to rewrite the next two numbers out beside it. Because y'all would do basically the same thing if you were doing this one in the homework. They'll tell you to find the determinant of this one. You'll have to write down the original matrix, and then you just tack on the first two columns, just rewrite them again on the end of it here. All right, and then we're just going to start multiplying. And again, you've got to multiply three numbers, so the first numbers you can multiply would be here. So again, the good thing is with the numbers, you get to multiply as you go. It's 3 times 4, which is 12. 12 times 1 is 12. We're going to add that to 5 times 6 times 0. Well, that's 30 times 0, so that's 0. And we're going to add that to negative 1 times 2, which is negative 2. And negative 2 times 3 is negative 6. All right, and then we're going to do minus all three numbers going this way. So we've got 5 times 4, which is 20, times 3 will be 60. All right, now, and if you're doing these and you're like, if your numbers don't quite match up when you're drawing these numbers and it gets a little crooked, when you're writing these numbers out, if you can equally kind of space them out so the spacing's all the same, the numbers will line up better. That was one of the hardest things I had to do when I was first doing this one, was keeping my numbers lined up, because I would cram this one in and space this one out and it would throw things off. So when you write out these numbers, if you can kind of equally space them out, it makes the numbers a little bit easier to see when you're multiplying. Okay, next one up. -1 times 6 is -6. Times 1 is still -6. And then going this way, 3 times 2 is 6. 6 times 0 is 0. Okay, so we've got, in the red up here, we've got 12 plus 0, which is 12. 12 plus -6 is -6. Minus, go in the parentheses and work on this set of numbers. 60 plus -6 is 54. Plus 0 would be 54. Oh, wait, that's not a -6. My bad. Whoops, sorry. That's 12 minus 6. So that's just a regular 6. My bad. Okay, so then it's just 6 minus 54. So that's -48. Okay, so for a 3x3 matrix, the hardest part really is keeping things lined up so that your numbers don't get kind of squished in one part and spread out in the other, because that makes the numbers easier. But if you've got everything kind of equally spaced out, again, it's just multiplying this way, and then you put a minus, and then you multiply this way, and then you subtract those two things together to kind of get the answer that you're looking for. Okay, now, last thing I'm going to show you. You don't have to write this one down. So I'm just going to flash up here to you real quick. What you do and how that works with finding determinants and inverses and all this other stuff is that, because in the first part we were checking for inverses to actually, and again, you don't have to write this down, so I'll just flash it up on the screen real quick. If you actually want to find the inverse of a square matrix A, that's like a 2x2 matrix, then what you have to do to find the inverse is that you go ahead and figure out what the determinant's going to be. So you go ahead and do the cross products where you do this times this and this times this, and you subtract those two numbers. And to actually find out what the inverse is, which is the A-1 part of it, then you take that determinant, take the value of the determinant, whatever it is, you put it as 1 over that, and then you multiply it by where you switch these two numbers, and then you change these two signs. And by doing that one, it will tell you what the inverse is, so that if you multiply it together, then you could, find out all the parts and pieces to go with that. So that's where we use the determinant, and that's how we kind of bring that in to find out what the inverse of it is. If you're talking like the actual applications of what you can do with that one, is that here's the actual application of this thing. To find the area of a triangle, if you know what the coordinates are of the 3 points of a triangle, then you can actually figure out what the area is using the determinant to figure out what it is, where you kind of do something like that. So this would be a question where they would say, find the area of a triangle with these 3 vertices. That basically you put your points in here. You put the first point, the second point, the third point in. This one's all ones. And then you go back and go through the formula and you set it up, and then you can find out what the area of that triangle is going to be without having to know any other formulas with this thing. So it has some applications to it that you can actually do in life if you're working with triangles and trying to find areas of triangles in different shapes. So.